symmetry has a magic power, both in our life and in science. And it's so versatile that the best way to address it is just to address some special subject. And today I want to show you how this power works in the world of large macroscopic bodies described by statistical physics or thermodynamics. So, first of all, I want to give you a quote of by a well-known great physicist about both thermodynamic and symmetry. And because if I say that I will present you thermodynamic and symmetry, so I'm not sure if maybe symmetry and thermodynamic. So let me tell you what Einstein was thinking about thermodynamics. You know that in the process of evolution and accumulating of new knowledge, the theories which were modern at some time, they get replaced by newer theory. They replaced and overthrown by newer theories. For instance, Newtonian mechanics has been overthrown by quantum mechanics and relativistic mechanics. But, and by the way, this revolutionary changes was to the great extent due to Einstein himself. But he is saying about thermodynamics the following. It is the only physical theory of universal content which I'm convinced will never be overthrown. In other words, he's saying that this is forever correct. It's so complete and so universal it will never be overthrown. Then let's quote what great scientists speak about symmetry. So Tsung-Dao Lee, he is a particle physicist. He says that since the beginning of physics, symmetry consideration have provided us with an extremely powerful and useful tool in our efforts to understand nature. Gradually, they have become the backbone of our theoretical formulation of physical laws, which means that we use theory as a tool, and then eventually we become to look for symmetry as a goal of our research. Right? Now, about my talk. So I have to confess that I've never been able to understand what is this kind of simple presentations which address you through your eyes, showing pictures. So I always needed to prove. I needed the ideas, and so in my talk I will give you mostly idea. I'm not going to impress you. If I still want to impress you, I would do the following. First of all, the symmetry cannot be visualized. So I forgot the word popular science. Right? Remember, I was saying, I forgot one word, popular science. I couldn't understand popular science. So, symmetry cannot be always visualized. So you cannot expect pictures. So to me, I can share most impressive fact related to the symmetry that I know. And this fact is that our main, most fundamental laws of nature and physics are the consequences of some symmetry. So, just want to ask you, what are the most fundamental laws of nature and physics? What do you think? Most fundamental. No, it is not a law. Law of nature is energy conservation, momentum conservation. Right? So, on this These are consequences of theory, of the some symmetry. Due to Emmy Noether, German mathematician, we know how to connect conservation law with the symmetry. Let me tell you what is the symmetry consideration looks like. Suppose we have some object and it depends on some parameter, right? And we change this parameter, but the object doesn't change. And then we say that this object is symmetric with respect to these changes. We call changes transformations. Right? So from Noether's theorem, it follows that if the laws of nature is the same today and tomorrow and at any other instant of time, then the energy is conserved. And then if the law of nature is the same here and here at any point of space, then it follows that the momentum is conserved. In other words, if our time is symmetric, then the energy is conserved. If our space is symmetric, then the momentum is conserved. So I can continue this, but to me it is really exciting. Right? But I cannot visualize this. No. And this is now outline of my talk. I will start from few body systems described by Newton mechanics. I will show the role of symmetry. Then I will tell you that the symmetry is actually the collection of invariant transformation. Then we will come to the many body systems, which are just large macroscopic systems described by thermodynamics. We will need to address the difference between small and large systems, and then we will be talking about relation order, disorder, symmetry, energy, and entropy. Then we will find out that the real state of large body sets in the competition between energy and entropy. We will introduce free energy, and finally we will arrive at the relation between symmetry and phases of matter and phase transition. I will introduce polar order and second order phase transition, and then non-polar nematic order and first order phase transition. So at the beginning we consider few body system. So this is some surface, and we put a ball on the side of the surface, and everybody knows what's going to happen. This ball will go down because there is gravitational force which brings this ball from the state with higher potential energy to the state with a lower potential energy, and then it will come to the bottom, and because of friction it will stop moving and will rest here forever. So it's stable state. Right? Stable state means that there is no force here. And let me show how this fact follows from the symmetry. Now, this situation is symmetric with respect to this axis. Suppose that we have force which is acting to the left. But because of the symmetry, then we have to assume that there is force to the right. Right? The same force, but in other direction. And then it follows that two forces, they cancel each other. The total force is zero. So this is consequence of the symmetry. And the stability is a consequence of the of symmetry. Now consider this situation, which is also symmetric, but everybody knows what happened next. If you imagine that you are on the top of the slippery hill, then you know what happened. You know you will find yourself in the ditch, here or here. So the symmetry again tells you that there is no force here. That's correct. There is no force. Force is zero. But any fluctuation incidentally bring you, well, where? Maybe to the left, maybe to the right. You cannot tell exactly. But what is clear that this symmetry, you see, it is broken. This situation is not symmetric, and this is not symmetric. So this symmetry, this state is quasi-stable, and the transformation of quasi-stable state is called spontaneously symmetry breaking. This is left stable state now, right stable state, but to which one you will come after this, you don't know. So in few body system, transformation are driven by energy, right? Minima of the potential energy are the stable state, right? That's minima of potential energy, they are stable. Maxima of the potential energy are quasi-stable state. Okay. Now, let's come to the consideration of symmetry. What symmetry is in physics and mathematics, actually. But intuitively we know that this is symmetric figure and this is asymmetric figure. But why? If you want to formalize what makes it symmetric and this antisymmetric. In the case of a symmetric figure, you can apply operation of symmetry which doesn't change this body. For instance, you rotate this figure about this axis by 180 degrees, and the result will be exactly the same figure. Or you have mirror here, and then you reflect this figure in the mirror, it will be exactly the same. So this is symmetry operation, and here you don't have symmetry operation. If you rotate this body about this axis at 180 degrees, you will have different body. So this is why it's asymmetric. So the symmetry in physics and mathematics is a collection of transformation which brings the figure to itself, or in other words, transformations that do not alter the figure. These transformations are the symmetry transformation or invariant transformations of some figure or body. Now let's consider what is the symmetry of these bodies. Now just use your imagination and experience. Tell me maybe what is the most symmetric and less symmetric figure. What do you think? Which one is most symmetric here? Huh? Circle. Great. So the intuition is very strong. Now why? But why? Because, for instance, this is a less symmetric figure because we just count the number of symmetry operation. What are the symmetry operation for this triangle? It's rotation by this angle, plus rotation by this angle, plus rotation by the angle, plus there are mirror symmetry about this axis, and this axis. And if we compare now the symmetry operation of this body, we realize that all possible operations, all possible changes do not change the figure. We can rotate it about any axis, and we can reflect it in the mirror along any axis and rotate it by any angle. It doesn't change. So this is absolutely symmetric. It's isotropic symmetry, absolutely the highest symmetry. And so now we consider what is symmetry of macroscopic bodies. Macroscopic bodies consist of huge number of molecules. So what is the symmetry then? look at this body, you see that this is symmetric, right? And this is not symmetric, okay? And actually it's opposite, right? But because the symmetry of this is much higher than this, right? Symmetry operation, so this is high order, but this is high order, and this is high disorder. This is liquid, and this is crystal. So now consider the symmetry of the body, which looks like intuitively it's symmetric. What is the symmetry operation for this body? We can translate this body, a crystal, along this vector to this point, and along this vector to this length. Along this vector to this length, we can rotate about this axis, which is perpendicular to the center of this disk by this angle. Right? So we calculate 1, 2, 3, many, but now this is isotropic liquid, and we can translate this point anywhere. It's still the same. We can rotate it about any axis by any angle. It's still the same. So isotropic liquid has the highest symmetry. So this is low symmetry but high order, and this is low order but very high symmetry. So this is probably a counter intuitive, but we have to adapt it because it's correct. Now we want actually to describe this transition from low symmetry to high symmetry, or from low order to high order. And to this end, we need to describe the states of macroscopic body. Right? We know that for a few body system, they're described by Newton laws. And to specify the state of few body system, we have to fix velocity and location of each body, and then it's fully specified. Now, what is the state of this large body? Now, to address this, let's think about air in this room. We know that the air, in the cubic centimeter of air, we have 10 to 21 number of molecules. Now, if somebody doesn't know what is 10 to 21, is 1 and 21 0, this number of molecules in small cubic centimeter. And we also know that these molecules are all the time moving. We know, moving. So that means that mechanical state, which is given by the coordinate of this molecule, and their velocity is changing all the time, changing. But do we see any change in the state of air? No, because there is no change. Right? So then we make this logical conjecture that if microscopic state is changing and macroscopic doesn't change, that means that each macroscopic state consists of many microscopic states, and then the system is in this microscopic state. It doesn't change macroscopic state. Right? So I want to illustrate it here. This is our space in which the state of our system, microscopic, is just one point. And small, if you see the small square here, blue square, each of this, if you don't see, believe me, it is here. So each of these small square is some microscopic state. So the molecules are moving stochastically. So this microscopic state is moving like this. Yeah? And sometimes it is in we divide the whole space into macroscopic states. 1, 2, 3, 4. So all these states which are here, if the microscopic state is here or here or here, you still have macroscopic state 4. If the microscopic state is here and here or here, you still have you see only macroscopic state gamma 3 and so on. Now, because this microscopic state is moving randomly, we randomly either on this or on this or on this or on this state. But we understand that if you have large number of microscopic states, then when we observe macroscopic state, more often we will see this state than this. Yeah, just the time we see this state is proportional to the number of microscopic states here. Right? So we say that the probability of seeing this state is proportional to the time we observe it. And so probability of having this macroscopic state is proportional to the number of macroscopic states and so on. So probability is proportional to the number of microscopic states. And then, now it's simple, right? It's simple, but this great man committed suicide because he's also great, and other physicists, also great, living at the same time. They didn't want to accept this idea. So, and you see at his tomb, this law is here. So entropy, we could, and there is no big sense in logarithm. It's just more convenient. What is sense is here, and the entropy is just logarithm of this number of states. So you see the log, and this Boltzmann constant, it doesn't play. It has no big meaning. It just because logarithm has no dimension. Entropy, which was introduced long before Boltzmann explained what entropy is. Actually, it has some dimension. So you need constant which brings this. It has dimension of entropy. Right? So. But why we see that our state in the air of air doesn't change? Because actually, when in the very large system, the number of states in one of these states is so much larger than the number of states in all other states that we practically see only one state, and this state is called thermodynamic equilibrium. Right? So in thermodynamics, we don't predict what is the state of the system. We predict the probabilities that we are in this state, because it's moving, and there is final probability that we are not only in the thermodynamic state, in the equilibrium state, but somewhere else. When we somewhere else, we say this is fluctuation. That fluctuation is small because entropy of this state is huge, and entropy of this state is very small. Right? That's why we see only one state. And what is important of this formula and this formula? In the microscopic state is mechanical state. So it's described by Newton mechanics. And in Newton mechanics is completely deterministic theory. It doesn't have any notion of probability. So this formula connects deterministic mechanics with the probabilistic thermodynamics. So it's a bridge. Right? It's a bridge. These are Newtonian state, and this is probability. So that's a great step forward. It was. Now, again, we still continue to want to describe the transition from high order to high disorder. now we know that energy wants to keep a molecule in the minimum, in its minimum, right? The minimum are well ordered. So if you energy wants to have crystalline state, but entropy, as we know, it wants to bring the system to the state with huge number of states, and clearly this number of states in this chaotic configuration is larger than here, because here you have any configuration they give you state, and this only very well ordered configuration. So, and in reality there are two tendencies. One is driven by energy, which wants to have order. Another is driven by entropy, which wants to have disorder. And now the actual state of the system is determined by the minimum, but not minimum of the energy, but minimum of the called free energy, which is energy minus temperature times entropy. So temperature is a controlling parameter which gives you balance between energy and entropy. If temperature is 0, then the minimum of free energy is minimum of the energy, and you have highly ordered state. If temperature is high, then you can just neglect energy, and the state will be completely chaotic. And at some temperature, which is called critical temperature, these two tendencies are balanced, and then we have transition from order to disorder state. Well, we know that ordered state, so from order to disorder, on from low symmetry to high symmetry. So this phase above T critical are disordered and have high symmetry, and the state below critical, they are ordered and they have low symmetry. So now I want to show you what is specific order and how we describe this transition from high order to high disorder. So we address specific symmetries. These two symmetries that I'm going to show you, they are in all the books. So they are paradigmic, most important symmetries in theoretical physics. One of them is called polar order. I forgot to tell you that there are two kinds of transitions. One is called first order transition, and another is second order transition. They are very different. I start from the second order transition. I will show you that this order results in the second order transition. I explain you what it is. So consider small magnets. Molecules have magnetic moment. So they are small magnets. We depict them as an error, because magnet is a polar thing, right? It has south pole and north pole. And the magnetic field of the system produced by this magnet depends on their orientation. In the isotropic phase, at high temperature, at highly disordered state, the total moment, which is the sum of this vector, is 0. Yeah, because the number of error up and down, they're the same, they cancel each other. At critical temperature, which is in this case is called Curie temperature, this error start to orient in average, not completely, I mean in average, you see that along some fixed direction. They chose this direction spontaneously, as I will show you. Right? So now there is direction, and now we consider the symmetry. This is isotropic phase. We know it's isotropic is highest symmetry. Now this symmetry is much lower. what is the symmetry of this phase? It's the symmetry of this magnet. If we rotate this magnet along the axis of this axis, then the magnetic field doesn't change. If we rotate it from about any other axis, then magnetic field is changed. So the symmetry is, and also if we change this vector, if we flip it down, then magnetic field, of course, will change to opposite. Right? So that's why it's called polar order. So now this is low symmetry state, this is high symmetry state. The problem is that we are talking and drawing pictures, and we need to put it in the mathematics. Right? So what is the mathematics? We know that the free energy, minima of free energy, gives you what they give you. In the few body system, they give you location, coordinate of the ball, right? Here, the free energy must depend, of course, on this magnetization, right? On this vector. So free energy depends on this vector. We have to find free energy as a function of this vector. And how to do this? Lev Landau gave us the recipe. He introduced order parameter. It's a mathematical object. So instead of this picture, you introduce mathematical object. And this object, we have to choose it. And how we choose it? This object, mathematical object, must have exactly the same symmetry as the macroscopic symmetry of this body. And the macroscopic symmetry of this body is described by this polar vector. Now, what are the mathematical objects we deal with? There are scalars, there are vectors, tensors, and so on. So when you change rotate the body, they are changing. Scalar doesn't change. What is the example of scalar? Density of our body. Density is the same. If you rotate or translate, it's still the same. But the order parameter, magnetization, is different. If we rotate the body, then it changes it. Right? So clear that vector is good candidate for the order parameter. And now vector of magnetization. Magnetization is total magnetic moment of the whole body. And the length of this vector gives you the strength of magnetization, and direction gives you direction of magnetization. Here's the problem. We want to write free energy as a function of vector. But free energy is just energy, which is a number. And vector is not number. So we need somehow to write possible expression for free energy in terms of vector. So this is scalar and m is vector. So we consider all possible way to make scalar from the vector. How we can make scalar from the vector. So m, just vector m, cancel, you cannot do it. That is its vector. But vector dot vector is a scalar product. Right? It's the length of the error, square of the length of this error. So this is array. This is scalar. So we can have it in the free energy. Then the square of this is also candidate. So and that's enough. It's enough because we consider that m is small, the higher order of m, they are even lower. So this is Landau's theory of phase transition. And it is very, very important that we cannot make m cubic. It is impossible to make scalar, which is third order in this magnetization. It is impossible. You see this? No m square. And then we have so-called second order phase transition. So we need to so this A, B, they are positive constant. And here we introduce the factor which is temperature minus temperature critical. Now, when temperature is high, what we have? This is positive, this is positive. This function is going like this. This function is also going like this. When we add them, we have branches are going looking up. But when this temperature is below T critical, then this coefficient is negative. And when it's negative, then it's still with branches up, but this is inverse parabola. It looks like this. And when we add this to this, I forgot to tell you that before when T is larger than T critical, we have this shape with the single minimum, and this single minimum in 0. So now magnetization is 0. But when this is negative and temperature is below T critical, then we see appearance of two minima. This minima doesn't exist anymore. We have two minima. Remember the picture I started from. It is exactly the same picture. So now this maximum is quasi-stable state. It was stable, now it's quasi-stable. So the system will spontaneously go maybe here, maybe here. What is important that when temperature is decreasing, the location of this minimum and therefore the magnetization is just increasing. So what we have, when temperature is high, then we have stable minimum with magnetization 0. And then when temperature is below, we have a quasi-stable maximum, and which spontaneously transform into what? One of them. If it go to the left, then we have magnet directed like this way. If incidentally it goes to the right minimum, then magnetization is just opposite. So here is M negative, and here it's positive. So you cannot say when you have this situation and you change the temperature, you don't know what is the direction of magnetization. You know the magnetization, but you cannot predict the direction. That's why it's called spontaneous symmetry breaking. What is important? This is second order phase transition. What is the benchmark of this transition? Important that this order parameter goes like this. At a high temperature, magnetization is 0. And then at some critical temperature, it starts growing continuously. And the lower temperature, the larger magnetization. Plus, what is very important, you can only have one minimum. This is M equal to 0 or M is finite. You cannot, there is no situation when the free energy is the same for M0 and for non-zero. There are two phases, isotropic and magnetic phase. They cannot coexist. You see, your magnet cannot be half isotropic, half magnetic. It can be either magnetic or paramagnetic. Paramagnetic means magnetization is 0. So this is the consequence. Why we have the second order transition? Because our order parameter, our symmetry, is polar symmetry, and we don't have cubic term here. So everything is fixed by these two terms. Now I want to tell you about another order which is called non-polar order. and in other words, it's nematic. In nematic liquid crystal is the most prominent example of non-polar order. What is nematic liquid crystal? So I give you some idea. For high temperatures, usually we have high temperature, we have isotropic liquid. For low temperature, we have crystal. But liquid crystal is a mesophase, is an intermediate phase between liquid and solid. So at some in some interval of temperature, the center of molecules are not, they are chaotic, but their orientation becoming more or less along one axis. This axis is called director. It doesn't have length because it just shows you the direction. It's like my finger. If you show the direction, you don't need to explain what is the length of my finger. It's just direction. So, and because these molecules are not polar, there is no difference between up and down orientation. So this is called non-polar. In comparison with the polar order, there is additional symmetry operation, which is mirror reflection in this in the horizontal plane, right? Because of this non-polar order. This is another. This is smectic. You see that molecules stay in light, just to show you another phase of liquid crystal. This is called nematic liquid crystal. This is smectic liquid crystal. And nematic liquid crystal, usually when you present, you say that, oh, this is consists of elongated molecule. But what I want to emphasize that phases of matter are determined not by the shape of molecule, not by their chemical structure, not by their physical properties, only by one thing, by the symmetry of the macroscopic phase. So if you, very good example of this is this. A nematic, which is composed of prolate molecule, and this is nematic composed of oblate molecules. No? They are very, very different, as you see. But the similarity is that they have this axis here, which is called director. So this is nematic, and this is nematic, and they have the same properties. You see that chemical structure doesn't play any role. That's why we have huge number of different compounds and only few different phases. We have crystalline phase, liquid phase, liquid crystalline, gaseous phase, what else? Few. But the number of different compounds you cannot even count. So the symmetry makes unification of them into phases. Right? So the phase is symmetry. Now how the symmetry works? It's a little bit more complicated than the case of polar order. I explain you why. If you have, because it's non-polar, therefore you cannot choose the director as the order parameter, because vector has direction. It's a polar. If you flip it down, it's a different. So you need something which is quadratic in the director. So this is tensor. This is called tensor. If you change sign of n, then you have minus here, and total doesn't change. So this is order parameter of liquid crystal. And also we have, instead of magnetization, we have this so-called scalar order parameter, which shows you the degree of orientation. When S is 0, they have isotropic phase, it's full disorder. If S is equal to 1, you have perfect orientation, which never happens, of course. And normally S minus 1 is some degree of orientation. So the order parameter is like this. And then, I don't want to give you details because it's difficult and it's technical, but you have to believe me that if you compose free energy, if you compose the scalar from this order parameter, you can have quadratic term, you can have quadratic terms, but you can also have cubic terms. And this cubic term changed completely everything. Again, what is the reason for this? The symmetry. The symmetry of polar phase doesn't allow this. The symmetry of non-polar phase allows. So we now have the following. For again, the same for all these constants are positive now, but for high temperature, we have single minimum here. And S, now free energy depends on the order parameter, right? For MS. And the minimum at S equal to 0. That means isotropic phase. When the temperature is going down, then eventually we have appearance of the second minimum. But this minimum is much higher than this. So the system doesn't go here. But at some critical temperature, this minimum touches the axis. That means that we have two minima, and they have the same free energy. And that means that the system can be here and here at the same time. And we therefore have coexistence of two phases. We can see both phases in microscope at the same time. Right? Then what further happen if one so this is very narrow range of temperature when they coexist, because these two phases, they are separated by this barrier. When the barrier is disappearing, the isotropic phase goes down here to this minimum, and the system is only nematic. So the benchmark of this transition is that order parameter is changing like this. It's going to critical, and then it jumps immediately to the final value, which is this value. And both phases can coexist. You can see here that this dark field is the isotropic phase, and these droplets, colorful droplets, are the nematic phase. They are flowing just within the isotropic phase. Here, this is isotropic phase, this is nematic phase, and this is the boundary between them. So you can see it in microscope. Another example, how important this is. Now remember that ice flowing in water. We know that for high temperature we have only water. For low temperature we have ice. But we also know that in some temperature interval we have ice flowing in water. Therefore, the water-ice transition is of the first order. Right? It is very complicated transition because we still have problem understanding water. But what we know about that should be first order transition, therefore it should be the energy, free energy should be of this kind. If we don't know, we have to somehow look for this. And another good example of first order transition, well known, it's a water vapor transition. We know with cold water we have water. With high temperature we have everything evaporates, right? And now we're asking so they can also coexist, as you know. There is vapor over the water. Now, so it looks like it's first order transition. Now, can we justify it from the symmetry consideration? Let's think, what is the order parameter of water and vapor? So it's isotropic liquid, right? There is no error, no vectors, nothing. The only thing that we can imagine is the density. Our density is scalar. So then, if we have scalar, we can compose any combination, because this is scalar and this is scalar. So we have n square, n cube, n to the 4. But at least this term is allowed. And if it's allowed, then we have exactly the same picture that in the previous slide. The only change is that instead of S, you see, I forgot to change this S. It should be N density. Right? So I change this as critical to N liquid, and this is N gas. It is exactly the same transition, and it gives you everything that I told you before. That now, when temperature is going down, you for high temperature you have N gas, which is very small density, and then it jump to the 1 gram per cubic centimeter, which is water density. Right? So you see that symmetry is a very universal thing. And what time is it? How much time do I have? Okay, great. So Einstein, remember I quoted Einstein, he was saying that this is like eternal theory. I didn't quote the beginning of this, of his quotation. At the beginning he was saying that thermodynamics is so great because from very few basic assumptions and ideas, it can explain so huge number of phenomena. So, and the reason for this, I believe, is the symmetry. Because symmetry unifies so many phenomena into just one bundle, and you have to explain, instead of transition from water to vapor or benzene to water, you just say this is isotropic liquid, it goes to vapor. So, yeah, what? So I hope my talk will help you to get some understanding of the relation between symmetry, order, energy and entropy, phases of matter, and phase transition. And thank you for your attention.
Thank you, Victor. Thank you for a great talk. I think that we'll have a lot of questions from the audience.
We will see.
Oh, I'm pretty sure that there were. Also, who would have a question to the professor? Oh, please.
Could you show us the slide number 4?
Number
4. Yes. We see here 3 configurations. Let's say this represents universe. So the very much to the left and the very much to the center are the same. This on the right is different. But all these universes has a particular configuration which represents minima of potential energy. This universe at the left has 1 minimum, and this on the right 3. So could we consider these points of minima of potential energy singularities or particularities? In other words, any state of minima of potential energy should be considered as a singularity?
Not any state. This is state of potential energy, and it's not singularity. It's stable state. But this is singularity.
But in terms of its quantities, it is singularity. There's no other any configuration in this universe except this.
Yes. In mathematics, singularity is when you smooth function, they have something which is called singularity. So it becomes, for instance, not continuous. Right? So for instance, this is I cannot write. Like this is smooth function, and then it becomes like this. This is singularity because it's derivative. If you take the derivative of this, it's smooth. If you take derivative of this, it jumps. So here, this point is.
It's not only mathematical; it represents some physical state.
Of course, it represents physical state.
In terms of physical state, is singularity, not in mathematical
then I just singularity. You mean singular? Is like only. You see that even after this transition, we have singular state, single state. We don't have two states. It's if this was stable universe, and then God said, no, it's enough. Let's make something new, and He produced the universe according to this mechanism of spontaneously symmetry breaking. Then the universe will be one only, because it will be either here or here. But if He decides to use first order transition for the giving birth of universe, and then we will have maybe many universes coexisting. So here it's still singular in your sense, but this is one state, and this is one state, and this state you will never observe. This is, if you see this state, it's you will see fluctuation, and then boom, it will come to some. So in that sense, it's still one state here and one state here. Another thing that you cannot predict which one, this or this.
But can we generalize this in terms of physics, that any state of minima of potential energy can be considered as a particularity?
It depends on how you perceive what is singularity. For instance, if you, as I told you, if you are on the hill and you see the trenches with water, that's very singular to you. You know, you want to choose the trench with less water, for instance. So it's very important. In that sense, it is important. But otherwise, I don't understand what you mean. We are sitting here. I'm staying on the floor, and I'm on the minimum of potential energy. If you remove the floor, I will go down to the another floor, and then.
Configuration now is a particularity, because there's no any other configuration in the universe like you.
Yeah, of course, I'm sure. Nothing like me. Probably. Yeah, so now it was promised that so many questions.
I have a question.
Mm-hmm.
Sometimes when I read about quantum mechanics, I come across the term symmetry group, and I always wondered what is it, and I don't understand the Wikipedia definition of it, of a symmetry group.
Okay. Remember what I said? Here. What is that? Symmetry is a collection of all transformation which brings the figure to itself. Right? And this collection of transformation, in the simplest case, it's a group, a single group. Altogether, what is group? When you take one element of this group, right? For instance, you have this body, like this body, and the symmetry group of this body is rotation by this angle. So that all these states realize their realization of this group. So the group consists of rotation by this angle, by this angle, by this angle, by this angle. Why it's group? Because all elements of this transformation you can obtain just from one rotation. Right? So this rotation repeated twice will be this element. Repeated 3 times, it's this element. But there is another symmetry, which is reflection symmetry, where all this exists. This is different group. But still, the collection now consists of group of rotation and the group of reflection. The group is also collection of transformation, but so to say closed group. And you cannot obtain rotation from reflections, but all reflection can be obtained from one reflection. For all rotation can be obtained from single rotation. That in mathematics is called group. So let me thank you again for your time.
Exactly. So let's thank Professor once again.